Okay, now let's look at the reaction module. In the reaction module, you have to set up your own reactant and the product. Then package will pull out the thermodynamic information related to the reactant and the product, and then calculate the enthalpy and entropy and the Gibbs energy of the reaction for you. So if you click the reaction module here, then you'll have the reaction window opening like this. So in the package, it always shows you the last calculation you have done. So in this case, as you can see, I did some calculation about the CAF2 in the previous stage. So if you want to start the new reaction, you can click this one, new reaction here. So let's click and say yes. And then it keep asking you, okay, what kind of database you want to use, but we can set up this one later. So you can always say yes. Okay, so here's the beginning of your reaction window. So whenever you do the thermodynamic calculation, either reaction or in the eclipse or in the phase diagram, the very first thing you have to decide is the unit of the, the thermodynamic calculation. And also you have to define what kind of database you want to use. So for example, if you click the unit button here, then it will show you this kind of the unit menu. So you can change your temperature, pressure, and energy, and also the quantity, actually, the unit. So for example, I want to set up Kelvin as my in this actual calculation as a temperature, and ATM for the pressure, and then Joule. And then if you are in the industry, you probably prefer to use the kilowatt per hour or BTU unit as well. And then quantity in this actual simulation, in this calculation, I prefer to use the mole. Okay. And also when you move actually this unit, you can see that in the bottom there's the conversion factor between the different units. So you can actually easily convert your result in terms of the other unit as well. Okay, say yes, okay. And then you have to decide the database. So for example, if you click the database, you can have the many database here. So this is the standard FXAG database. Any database you can use based on your license will be white actual color here. And then something gray, it means you don't have the license for this kind of database. So it means even I want to click here and the mouse left click, but it doesn't activate it. So whenever you click here, then it activates. It means it will include this database in your calculation. Okay. So you have to decide which database you want to use. And then here there's the so-called private database. So for example, one of the database you generate in the compound module can be also shown here. And also if you make your own solution database, that will be also listed up here. And sometimes if it is not automatically listed here, then you can click this one, add remove database, for example. And then if you click add, then you can browse your database and then say okay, then it will going to connect to your thermodynamic calculation. Okay. So in this calculation, I'll prefer to use the very simple data. So I want to just use the packed PS database. By the way, as you can see here, the greenish color behind the actual as a background for the database means this have the only compound database. And then if this is the only yellow, it means it is the only solution database. And then if you don't have the color, that means you have the both compound and the solution database as a package for each of these actually database. And then as I told you, the gray color means that you cannot access to this database. Okay, so when I click this one, pack the PS, and in the bottom here, you can see if you look at this window here, you can see where this database is located, and then what kind of database it is. And so this one is compound database, and then it's a packed PS, packed pure substance database 2020. That's what it is. Okay, let's say okay. And then now you have to set up your species here. Okay, so let's just start with this one. Let's say I have aluminum. Okay, so you can both make a reactant and a product. So for example, this, if you click this one, it will make more reactant. If you click this one, it will make a product. So you have reactant equal to product. Okay, so let's start again from new reactant. So yes, so I'm using aluminum as a reactant. And then you can define now the phases you want to actually use in the calculation. So most stable, if I click the most stable, it means at the given temperature, it will pull out the most stable phase. So for example, you can have the solid below about 750 degrees Celsius, and above 750 degrees Celsius, it will become liquid phase. And then if you go to the very high temperature, it will become gas phase. So depending on the temperature you are adding, it automatically tell you what was the most stable phase, and then take there actually the thermodynamic property in the calculation. Or if you don't like, so for example, if I want to calculate aluminum solid Gibbs energy at 800 degrees Celsius, then you have to just take a solid. Or if you want to see the undercooling of the aluminum below, for example, 400 degrees Celsius, you have to take a liquid as a standard state here. Okay, so let's start with the most stable. Okay, so typical reaction calculation, you need both reactant and the product, but you can also do this one. So I have only reactant, and then click next, and then you can set up your temperature, for example, 300, and then space, it means I want to do the more than one calculation, 1000, and space 100. This means I want to do the thermodynamic calculation of aluminum at 300 degrees Celsius to the 1000 degrees Celsius with every 100 interval with temperature. Okay, so now if you click the calculate, it will show you what's the thermodynamic property of the aluminum, pure aluminum, 1 mole of the pure aluminum, because it's 1 at the different temperature. So as you can see here, so from 300 degree to 933 Kelvin, it is aluminum solid state. So you can have H, Gibbs energy, and etc. So this is the Gibbs energy of the pure aluminum at the different temperature. And then it will have the phase transition at the 933 Kelvin from solid to the liquid phase, and then it becomes liquid phase. So at here, PACSage automatically know that this aluminum is liquid state, and liquid aluminum is most stable state. So it will give you the aluminum for the liquid state, the thermodynamic property of aluminum of liquid state. Okay, so you can do this one, and then once you have this kind of information, of course you can have the output, and you can save all this one as a text file or print it, and then also you can go to the figure and the make axis and draw the diagram if you like. So now let's go back. And so if you don't like this one, if you want to have the new calculation, you can make it clear, and then you can add another temperature if you like. Okay, so now let's go back to the previous one. So that was the most stable. But now compared to that, if you take only solid, okay, and then if you go to the next, then if you do the same calculation, now it will show you aluminum solid Gibbs energy or enthalpy and thermodynamic property even at the 1000 degree Kelvin. Okay, so this is different between the most stable state or the given state of the given actually the solid or liquid state. Now let's go back. So this is the most simple one. So you can even check the thermodynamic property of the any species at the given temperature in this way. Now let's add product. So this is the reactant and this is product. So let's say I have aluminum become aluminum, for example. And then let's, for example, I say aluminum T instead of like this, 298 Kelvin. So it means I have aluminum solid 298 as a starting point, and then my product is aluminum in the most stable state, or you can change it if you like, but I'll keep most stable at the given temperature. So it will give you the difference between your reactant to the product. So product thermodynamic property minus reactant thermodynamic property will be given in the calculation. So next, then now let's say 300 degree or let's start, yeah, okay, start in this way, and then do the calculation. Then what it's doing is, okay, I have reactant at 298 Kelvin as a solid state. So this is fixed. And now you are changing the temperature of the product, and then it will give you the difference between these two. Okay. So it will show you like this. So for example, if you want to, so this one is related to the reaction. So let's assume I have 25 degrees Celsius aluminum solid. I want to increase temperature of aluminum, okay, until 500 degree Kelvin. So until 500 degree Kelvin. How much heat I need? Delta H of this reaction. That's the amount of heat I need to increase the 1 mole of aluminum from 298 Kelvin to the 500 degree Kelvin. Is that okay? And then if you want to actually make it as a 1000 degrees Celsius, it becomes liquid phase. So you need all this enthalpy in the solid state, and then melting enthalpy, and then even increase the temperature in the liquid state. So you need this amount of the enthalpy, this amount of energy to make aluminum from solid 298 Kelvin state to the liquid at 1000 degrees Celsius, 1000 degree Kelvin state. Is it okay? So you can easily calculate the amount of heat you need to increase the temperature or decrease temperature. Okay. So this is the very simple one. Now let's start making something like this. So more chemical reaction. So for example, like this. So I have aluminum solid and then oxygen and make Al2O3. So this is really the oxidation reaction of the aluminum to make alumina. So what would be the reaction Gibbs energy, for example? So we can calculate something like this. So let's set up this one. So new, okay, yes, okay, yes. And then I have two reactant, I have the one product. So here I have aluminum, oxygen, and Al2O3. So you can set up first what's your species. And then if I want to really start with the solid, I can say solid, and I have gas, and then this is also different solid phase. So if you have the more than one solid phase, it will show you all the different solid. But I know S4 in this case, solid 4, corundum is more stable in the room pressure condition. So I just take this one. So now if I just do this one, I intentionally leave this stoichiometry. Uh, Not, I mean, I didn't actually put the correct stoichiometric value here. And then if you just click this one, facts say that, okay, reaction is not balanced. So means you cannot make your product from the reactant with this amount. Yeah. And then it will say that, do you want to automatically balance this reaction by the program? If I say yes, then it will automatically make a balance like this, as based on the first reactant. Okay, so 0.75 becomes 0.5. If I don't like it, then I can go back. I say I want to have 2 and then 1.5 and then, for example, 1. I want to do the calculation based on 1 mole over Al2O3. Then you can do it in this way too. And then go next. And then you can set up your temperature. So for example, let's just keep this one as it is. 300 degree to 2000 degree every 100 degree Kelvin. And then if you do the calculation, it will give you all this calculation result. So here, as you can see, 300 degree, what's the delta G naught? And then all the way up. So all this delta G naught is negative value. Okay. So if you recall the Gibbs energy of reaction, delta G equal to delta G naught plus RT ln K. If the delta G naught is negative, okay, so in this case, if I assume pure aluminum, pure oxygen, pure Al2O3, that means delta G is same as delta G naught because RT ln K, the K become 1, so the second part becomes 0. So delta G is same as delta G naught for the reactant of all the pure species and 1 atm O2 and then pure Al2O3, then delta G equal to same as delta G naught of the reaction. Then as you can see, delta G is negative value. So that means we have always the forward reaction happening. So when you mix this together at the 1 atm O2 condition, you always make Al2O3 in any of these temperature. That's what it means. Okay. And if you copy this one, so for example, you can even copy this one by doing by click the mouse left button and then Control C, and then you can go to the Excel file, make Control V, and then you can make your own temperature, Gibbs energy, G naught, delta G naught function or enthalpy function, and etc. So it's very easy to do to make it. Okay, so this is the given as a temperature. Also, you can actually set up other the variant. So for example, let's clear. Is there any possibility I can make a delta G naught equal to 0? So for example, then I can remove this variant. I want to know when is this reaction become Gibbs energy of this reaction become balanced considering the pure species. If I say 0, then calculate. Then it say that, okay, if you assume aluminum as a solid phase, and then O2 as a gas phase, and then Al2O3 assuming it keeps staying as a solid phase, then about this 5,900 degrees Celsius, at 5,900 Kelvin, the delta G naught become 0. I mean, of course, this is theoretical value, and at this temperature, solid and the gas is, I mean, solid, aluminum cannot be solid, Al2O3 cannot be solid, okay? So this is also possible. Okay, let's continue. Let's now move on to the next example. So say new, yes. I want to do the calculation for the aluminum and calcium become, no, aluminum and silicon, no, calcium and silicon become calcium silicon 1,1 compound. Do you recall we made actually calcium silicon compound previously? So I'll go data search. I'll click this one and I'll also include my own database, InHo database. If you go to the actually compound, actually the example, we actually create a InHo database which containing CaSi11 compound. Okay, I want to do, so in this case, I want to actually combine two databases in the calculation and then say okay. And then let's set up this one. So here I have calcium and silicon, and then this one is CaSi. Okay. So if you look at this one, let's take solid one, and then let's take this one and the solid, and then this one. Okay, so here's the two database. One is PACT-PS database, have this data, and the other one is InHo database, the private database we create, also have this data. And then let's just remove this non-equivalent state. Okay, so we have the equivalent, just the standard state, calcium silicon become calcium silicon 1,1 compound. And then go next, and then let's click 700 degree Kelvin, and then let's do the calculation. Then you see at 700 Kelvin, delta H was the minus 10,000 joule, and then delta S was minus 5 joule per Kelvin. This was exactly the same as what we prepared before. So for example, to equal this one, we make this one in the compound actually module. So we set up this new CaSi with this condition, and then we generate a private database. So here H and the S, and this is exactly the same as the H, delta H, and delta S here. Okay, so I think this give you the very brief actually the idea about how to use the reaction module. So what I want to actually highlight here is the reaction module. In the reaction module, you have to set up your input and the output, reactant and the product. Then TextEdge will pull out the thermodynamic information for the reactant and the product. And then if you give some final condition like a temperature, then it will give you what's the delta H of the reaction or delta G of reaction. But most of the time, in this case, you can use just the standard state. So it means the value you get is the delta H naught, standard state value, and delta G naught for the pure standard actually the material. So pure stoichiometric material value. Okay. So this is very academic kind of the application of the FACSH. Okay. Thank you very much.